Hi everyone, I'm Emily. This is Samir and Anne and Mohammad, and we're Group 7, and we're here to talk to you about our idea of building a private video recommendation system for kids. It's not a surprise to anyone that children use the internet, and it's growing increasingly common. A recent study from the National Center for Education Statistics determined that 64% of kids in the US under the age of 18 use the internet on a regular basis. And if you break that down into age categories, 40% of kids under 5 use the internet on a regular basis. That's a lot of kids. Because children are young, naive, and special, there are a lot of data regulations in place to attempt to protect children's behavior and identities when they're online. In 1999, the Children's Online Privacy Protection Act, or COPPA, was passed, and it was revised significantly again in 2011. The point of COPPA is to ensure that online retailers and other providers provide reasonable standards for protecting children's privacy and don't collect any private data on children without parental consent. In particular, one important line of COPPA relevant to us is that they need to establish and maintain reasonable reasonable procedures to protect children's data. You would think the existence of this regulation is sufficient to motivate retailers to provide such protection, but it's not. In 2019, actually in September, Google was hit with a $170 million fine because they didn't protect children's private data on YouTube. What they did was use children's data to provide content recommendations to them on child-specific YouTube channels. So that is a problem, and now Google is tasked with figuring out how to fix that problem. If you don't recall, we're just going to do a quick overview. So pretend this is my nephew Jay, who really likes watching YouTube videos when his mom lets him, and Jay also really likes breakfast. So he's there just chilling, watching some videos, but his video is about to end, and he's going to want a suggestion of what to watch next. So behind the scenes, YouTube is basically a recommendation algorithm. So it's figured out from Jay's history and from perhaps some other, or maybe a lot of other data points given their recent lawsuit, figures out that Jay likes breakfast food and so recommends, hey Jay, you should watch this pancake video next, and serves that up to him. Under the hood, as I alluded to though, these recommendations are currently based on a lot of personal data. The nature of that data is kind of unclear since YouTube stuff is generally proprietary, but studies have shown that it tends to be perhaps browser cookies or other browsing history, as well as age, location, gender data, etc., that is fed to this recommender system to produce the recommendations. And as we know, COPPA doesn't allow that to happen, so there needs to be a better solution to this issue of content delivery and suggestion for kids online.
So our solution here is to actually enable a system where you can actually give users privacy. So in particular, her nephew, he can send his encrypted data to these to the recommender system, and actually get back a response which is also encrypted and then locally decrypted. So he can still get the service which he wants while having privacy of his data. This also makes it inherently compliant with like these kind of regulations where the user's data never is revealed to the recommender system, and this makes everyone happy. Let's dig a little deeper into what the solution would look like. So on the left we have the nephew, and let's say he wants to have the next video, the recommendation on the next video. So the first thing he does is he encrypts his data. Like as soon as he requests that, hey, I want a new video, like the data is encrypted and sent to the server. Now the server could be a SEAL or a Navy SEAL or Kim's laptop. and then as soon as that's done, the server would actually compute over this data to generate the recommendation, and then this computed recommendation would be sent back. Now this is encrypted here and then decrypted on the user's device. And that would enable the system. A bit more on how this recommendation computation actually works is the user has a database of the movie corpus is of size M, and so we have M movies, and the user has seen a small fraction of them. At the server side, we have a matrix M by M, which in some sense is the machine learning part of it, where it knows the similarity matrix in some sense, and so it's a matrix there, and the computation is simply just a matrix vector product. And at the end of it, what we get is effectively different. So the product of this should ideally be a vector, which is of size m again. And that's what we want to feed back to the user, because this vector contains in different components the predicted rating of this particular user. What we end up in HE is we have each of these are summed up in a single slot. And so the first step is to actually get them in different slots and actually add them up into one single vector. And then the final step would be actually a very interesting bit where what we realize is these recommendations usually are very close to each other. So we have to do a small boosting step where we actually increase the gap between like the highly recommended videos versus like the less recommended videos. And so we do that, and then this vector is sent back to the user, and it's decrypted locally on the device to generate the recommendation. Okay, we would like to do a quick demo.
So in order to implement a demo of this system, we used an online freely available data set called Movie Lens, which has ratings and movies in a large publicly available data set. We use that to train a small recommender matrix, as was shown in the previous slide, and then we implemented this encrypted multiplication recommendation system in SEAL, which Samir is about to show.
Okay, so this would be the first interface where the kids felt very welcome that you need new recommendation on the video. You press a key, and then it gives you a very nice positive feedback. The user's data is actually sent to the server. There's some detail on the size, and I think it doesn't go too far. I think it goes maybe halfway to the page. So it takes a little bit, and the server is right now doing the computation and generation of the recommendation as well as boosting, and that's the time. And then at the user's end, you'd get back a recommendation which would tell you what's the next movie to watch. And then you have nice options to actually watch the trailer or get another recommendation. So I think that's pretty much it on the demo end. I think so this is a quick summary of our study on the feasibility or on the social aspects of this particular problem. So in particular, I think there is a huge social incentive for companies such as YouTube or Netflix to actually have an image where they do respect these laws and they want to be compliant. And so that would be our target application. I think this problem of recommendation also applies to other target domains. And I think I would let Emily talk about the insurance one.
Yeah, we thought a little bit about other contexts in which private recommendation systems would make sense. One major one is the US government's mandate that under the Affordable Care Act that citizens have health insurance. Currently, the US government has this open marketplace website where you go in and you input a lot of personal information, and then you receive a recommended insurance policy that you should purchase under the Affordable Care Act. But as I noted, that requires a lot of personal data input that's frankly unnecessary and could be done in an encrypted recommendation form, as we've suggested today. And then also online dating similarly requires a lot of input information, and it would be kind of fun to see if this sort of privacy-centric system could work in that context as well.
Yeah, I think with that we'd like to thank you for your attention and happy to take questions. I think, can I have Mohammad and Anna as well? Yeah, for the questions like this. Yeah, I think you can just move this.
So what is the boosting step exactly?
So the boosting step is we actually just take powers, and it's from the paper we were talking with Yongsoo, where if you want to actually take the max of certain number array of elements, then what you do is actually just raise it to the power, and so the gap between like the largest versus non-largest becomes different. So I think we tried to do so we couldn't get the end-to-end pipeline done, so we actually did train in clear like this a movie corpus. So we took a giant movie corpus. I think Anne can give more details on it, but we trimmed it into about 2048 movies and just used that corpus to actually train this. And what we noticed was you have like, so what we did was we did this synthetic examples where you have a user and this was a part of the training data, and then you remove one of the watched movies, and then you feed that vector in, and then you see that do you actually get a high recommendation on that particular movie, which was rated 5, let's say. And there we notice that, yes, you do get it roughly close to what the other 5s are looking like, but it's still very close to the other recommendations as well, and so we want to increase that gap. And yeah.
I would like to add one more comment about this boosting. So if you don't do further computation after boosting, I think similar to the sigmoid case I mentioned, actually the information is equivalent. X and X.
It's monotonic, yeah.
Yeah, so I think we don't have to run this expensive boosting process on the cloud, but just you can return X.
I think we had very high goals. Actually, we also wanted to run a adversarial machine learning attack on this, but I think one benefit so this is all empirical, but CKKS being inherently approximate, I think it also, the more powers you do, like it makes it more approximate, I think, but yeah, like it's a completely valid comment, I think, what you have.
And the other question is, you took YouTube as an example, but I don't think the real recommendation algorithm is not that simple.
True.
Yeah. And the number of videos on YouTube is kind of much larger than the user vector dimension. So.
Yeah. So regarding the algorithms, we took 2 different algorithms, collaborative filtering and content-based filtering. These are very simple algorithms, but very widely adopted. Also, in the scenario of video streaming, user can be active. So if you have some kind of hybrid solution later, we can also incorporate more complex algorithms to provide better service to the client.
I don't want to add that, for the sake of simplicity, the data that we have access to just contain movie ID, user ID, and then ratings. But, and then, of course, because of the universe of the movies that huge, and the number of videos at YouTube is just way too large, what we can do is we can bean the videos and then not training on just the rating, but training on features like category and certain other tags. So you can essentially compress that matrix a little bit. And that's the difference between the content base and the other collaborative rating, depending on what kind of data underlying your data set, you pick which algorithms.
So do you think it is fine to reveal that partial information about category or?
Yeah, we actually have a talk on this. The only core information that we want to protect, the user data, that is the only part that we kind of need to do the encrypted on. The other, some of the information can be public, which is like, let's say, the average rating of the movie, that is not something we need to protect. So that can be kind of extracted out of the homomorphic encryption part.